Good afternoon, class.
Good afternoon, sir.
Good afternoon, sir.
How was the Easter break?
It was fine, thank you, sir. How was your own, sir?
Fine, thank you. I know you'll be very glad that one class was skipped because of the break. You can't even like. Okay. The good thing is that you enjoyed the break and we are back. And we just have to move as fast as we can. I noticed some of you have watched the video, the YouTube video of the recording of last class. So I would, if it is possible for that of today as well, is to be put in the channel. And I encourage you to also subscribe to the channel so that, because very soon I will be adding some contents that would help in explaining some areas. And up till now, I've not received any question. It seems this course is just too simple that you don't even have any question whatsoever.
No, sir.
But I've not, the discussion board, it's not functioning. The emails I get is about how do I submit my assignments. I cannot access my LMS page. I've not really gotten any question that will say, how do we handle this? How do we treat that? So that means everything is very straightforward. So it's good to note. And okay, so like I said, there are some things, if you ask questions, I can make some videos and upload it on YouTube so that you can always watch. So that will be, that will start if you ask questions anyway, or if I see that this thing you need it. But there are some things I would not really know you did if you do not ask. Okay. In the last 2 classes, okay, this should be our 3rd class. In the last 2 classes, we spoke about, we started with heat capacity in trying to describe solids. And we spoke about Boltzmann's model. We went ahead to Einstein, to Debye. After dealing with Boltzmann, we said that Boltzmann has some limitations. We left Boltzmann, we moved on to Einstein. We also said it has some limitations. We moved on to Debye. We also said it has some limitations. We are moving again to other things. And it should spark a question that if they have limitations, why do we have to bother ourselves studying things? Why not just move to the one that is very okay and forget about the things that have some shortcomings? But if you go through your elementary physics or even elementary science, elementary mathematics, there are some things that you need to learn and later unlearn. But the things you have unlearned will serve as a foundation for you to build the new things on. There are some things that you learn, and though they are not completely correct, but by learning them, as long as they serve as an approximate value, they help you to understand the concepts better. For instance, you learned Newtonian mechanics in 100 level or even from your secondary school, but very soon you start seeing that even the Newtonian mechanics, you must have seen that at 20 level, that it also has some limitations. And in your primary school, they must have taught you that 5 minus 3 is 2, but 3 minus 5 is impossible. But later they will tell you it is possible. They will move on to secondary school, they will tell you square root of 9 is 3, but square root of minus 9 is impossible. They later come back to tell you that there is something called imaginary numbers. And you now begin to wonder, why did they now lie to us in the beginning? But if they have not lied to you, you may have gotten everything mixed up from the very beginning. So in this class, okay, the last time we spoke about the Debye and the we spoke about the Debye model. We stopped at the Debye model. So today we'll be moving on to electrons in metals. Okay, I'm sure we stopped there last class, right? So if I should ask, what are metals? One of the first things I expect you to mention about metals is to say that they are good conductors of heat and electricity. And why do they conduct heat or electricity so well? We move on to say because they have free electrons. Their electrons can move freely. They are not like tightly bound to the. They are not tightly bound like that of insulators. So, to understand materials better, the electrons in metals was also studied and also studied using different approximations. One of which we'll be talking about right now is the Drude theory. In 1900, Drude applied Boltzmann's kinetic theory of gases to electrons. I'm sure you must have learned the kinetic theory of gases, where you talk about the gas atoms or molecules moving within the containing vessels, colliding with one another with their containing with their container as well. The same thing, the same approach was now taken by Drude to now say that let us talk about these electrons as moving around like gases, colliding with one another and with their containers as well. So now, by just thinking about that, you know that at the end of this subtopic, I'll still come to tell you that there are limitations. But let's take our time and ensure we understand this part of the course. So Paul Drude's approach was to assume that Paul Drude came about with three assumptions. Excuse me. Okay. Assumption one, that electrons have a scattering time tau, and the probability of scattering within a time interval dt is dt over tau. The scattering time is tau. Scattering time is the time between two scattering events. So when two atoms collide, we can say they are scattered between that time to when another one will collide with another one, will say another scattering has occurred. So electrons have a scattering time tau, and probability of scattering within the time interval dt is dt over tau. So that is assumption one. The second assumption is that once a scattering occurs, the electrons return to momentum zero. That is, momentum is P, that is P will drop to zero. So every time tau would expect a scattering to occur with, would expect scattering to occur with the probability dt over tau. And once the scattering occurs, we'll expect that the momentum should drop to zero. And the third assumption is saying that in between scattering events, the electrons respond to externally applied electric field E and magnetic field B. So looking at these three assumptions, if you will have any problem with any of them, you shouldn't have any problem with this third one. That is, electrons, like we have known before now, are known to respond to electric field and magnetic fields. Okay, so in the kinetic theory of gases, we can estimate the scattering time based on velocity, density, cross-section of the gas molecules. So we can put assumption one and assumption two together. I'll put assumptions 1 and 2 together. We can come to this statement to say that the tau, which we have here, is the probability that an electron will scatter to momentum zero. The tau is the probability that an electron will scatter to momentum 0. There is a probability that an electron will scatter, and this is the momentum after it has scattered. So the probability that an electron will scatter to momentum 0 should be the tau. Please, if you have any problem, any question, if you get lost at any time, please raise your hand immediately. Don't let us be wasting precious time and data and a lot of other things. So the probability that an electron does not scatter to momentum 0, what should that be? Then we should go to think about something very elementary. Let's think about something very elementary. Let's say that the probability of you, let's say there are let's say there are 10 fruits in a basket, 7 mangoes, 3 oranges. What is the probability that you pick a mango? Usually we can say that is 7/10. Then what is the probability that you will not pick a mango? That should be 1 minus 7/10. So if the probability of scattering is dt over tau, then the probability that it will not scatter should be 1 minus dt over tau. And when we know the probability of things in science, we can easily do some further estimation. Let's move to the next page. So let's remind ourselves Newton's second law, which says that the rate of change of momentum is directly proportional to the applied force. Equation 31. Then what I was trying to say earlier is this, which is, what is the thermal average momentum after scattering? What is the thermal average momentum between a time t and a t plus a t? Sorry. So what is the average? This is the average momentum at time t. Then what's the average momentum at t plus dt? So we know that at time extra dt, scattering would have occurred. When scattering occurs, this is the probability that it will scatter. The probability that it will not scatter is 1 over the t over tau. The t over tau is probability that it will scatter. 1 minus the t over tau is probability that it will not scatter. When it scatters, it drops to momentum 0. So we can say 0, because the momentum, we are interested in momentum here. So we can multiply the momentum of it when it scatters times the probability of it scattering plus the momentum if it doesn't scatter times the probability that it will not scatter. So when you so this is the probability that it will, sorry, this is the probability that it will not scatter, and this is the momentum that we'll have if it doesn't scatter, because initially it was at it has a momentum p at time t. Then after a certain time dt, there will be a change of momentum, which should be dp, which should be equal to f dt. That is exactly what equation 31 is saying. So from equation 31, we can say dp is equal to f dt, and coming here, replace this, replacing the probability that it will not scatter with the probability, so replacing the momentum if it doesn't scatter as the initial momentum plus the change in momentum, the initial momentum plus change in momentum to give us the final momentum if there is no scattering. So when we expand this expression, we have equation, the equation that follows. This drops to 0. So what we have in the next line is an expansion of these two brackets. So when we get to so the t is the time interval, and the t is very small. On expansion of these brackets, we have a p of t dt. We also have a f dt times the t over tau to give us this one that I painted in red. But this term would be approximately 0 because the t is very small. And since it is very small, the square will be very, very small. And when it is very, very small, it may make no difference in our estimations. So that is a sufficient excuse to drop this term and come here, collect like terms, and now later arrive to the p, the t, t plus the t minus p of t, that is the t, the p, and dividing by both sides by the t, then we arrive at equation 32. So the force in equation 32 is the Lorenz force. So the force here is Lorenz force. Ayla?
Yes, sir. The red part that has plus f dt square over top.
Yes.
Plus, how come do we get plus over there, sir? I don't understand that plus.
Okay. Thank you. P times 1, that is P of t, and f dt times 1 is plus f dt times 1. This minus sorry, what is this one? What is this? I can't hear. So f dt, okay, sorry, p times this is minus, and the f dt times this should be minus. Sorry, it should be minus. Thank you for the observation. This should be minus, and if it is plus, if it is minus, it will still amount to the same thing. It is not significant. I will correct it, and thank you for the observation. So this is minus, though when it's minus, you'll still be talking about a small dt square, which is approximately 0. If it is plus 0, if it is minus 0, it makes no difference. So I hope that is clear. So, yes, thank you. So the Lorenz force, which you may have seen before, is defined in equation 33, and equation 33 is equation 33, which talks about the charge of electron multiplied by the electric field strength plus velocity times the magnetic field strength. So the scattering time is which is minus p over tau. This is the scattering time. Is described as drag force. When you look at this expression, this is like a force stupidity. This is also a force, so you cannot add force or subtract another thing from force. The units of what we have here should also be like a function of like having a unit of force. So when you say F in a direction, and this is minus, so it is like it is acting in opposite the direction of F. So it is described as the drag force on the electron. So we'll be working with this expression for now, which says the P dt equal to F plus P of t over tau. And our F, which is Lorenz force, is defined in equation 33. We can, so we'll be considering this expression when there is no electric field or magnetic field. We also consider it when there is no magnetic field and just electric field. We'll also consider this expression when we have the presence of both electric and magnetic fields. So when electric field is 0 and magnetic field is 0, the entire equation 33 will be as good as 0. So F here will be 0, and substituting F for 0 here, we can easily obtain our P of t to be P initial exponential minus t over tau. So I expect I should even give you this as an assignment to derive this expression from this. So let's take that as an assignment, derive this expression. So derive this expression. Is it numbered? Okay, it's not even numbered. Derive this expression from this. Oh, sorry. I hope that is clear. So I would expect you to submit via email. So now let's talk about electrons in an electric field. In an electric field, only, when we are talking about an electric field only, this is our equation 33, would be as good as we saying F is equal to minus E plus, so it will all become minus E. So the Lorenz force, when we have just electric field and there is no magnetic field, is as good as minus E, big E, minus electronic charge times electric field. So that is why we have this expression. So now we'll be considering a situation at steady state. At steady state means that the P dt is equal to 0. When the P dt is equal to 0, we are going to have something of this nature. 0 equal to minus E minus P over tau. And our P is also, our P is as good as mass times velocity. So from this expression I've written, you can easily obtain equation 35. So if the electrons in the metal have electron number density n, electronic charge E, and moving with velocity nu, the electric charge density or the current density is defined as J. J is equal to minus E n nu, knowing that n is charge density, and the charge density is as good as something like a charge over volume. And if you and J is also can also be defined as current density, and current density is something like current over cross-sectional area. And when you know that your current is also product of charge, charge over time, rate of change of the rate at which charges flow through a particular point, Q over T. So if you play around these equations, you should not say anything new with this particular expression. But you can now move ahead to say that you want to make nu, which is the velocity. You want to make nu to be the subject of the formula. And when you want to get nu, you can always obtain nu from this expression. From this expression, you can have your nu to be equal to minus E tau E over M. So when you substitute this value for nu in this particular equation, then you have the foremost right-hand side of this equation. And like I have defined J to be as a current over area, it can also be defined as products of conductivity and electric field. So that is, so when we know J to be product of conductivity and electric field, and we also know J to be a product of this fraction and electric field, then we don't need a babalao to tell us that what we have here is as good as conductivity. So, and that is the expression we have in equation 36. So, we'll deal with electrons in electric and magnetic fields. Then the Lorenz equation will be used completely. So that is why our F from that equation that I circled earlier that we'll be using, our F is now used completely, like the complete Lorenz force. And from this, we can go ahead and repeat what we did not long ago by saying at steady state. So we'll do the same thing over here and say at this point too, at steady state, what should we expect? So at steady state would also mean the PDT is 0. So at steady state, the PDT is 0. So we have 0 equal to an expansion. Okay, let's me move back a bit. Expression. I'd like us to export this expression to the next page. Okay, sorry, I can just do it like this. Let me just write it here. Zero equal to minus E plus no cross B. This is not just the multiplication, it is cross product. Minus P of T all over tau. Good. So the same thing applies here now. So the only difference now is just simple expansion that I expect you to play with. I don't know if I should even add this one to the assignment. Yes, let's add this one to the assignment. You have not been working, you have not been asking questions. The assignment 2 is that show the steps used in deriving this expression. Then from here, how did we arrive at this point? So the long and short right now is to say that in this expression, we have different terms. The two terms on the right-hand side of equation 38 are the perpendicular and the parallel electric field. So this is the term that is perpendicular to the electric field. Sorry, let me bring out the spotlight. This term is perpendicular to the electric field vector, while this is parallel to the electric field vector. So, and this should now take us to what we have known before. Who is speaking?
Sorry, sir, the last statement, the perpendicular aspect you just mentioned, I don't understand, sir.
Okay. Okay. Yes, sir. When let's consider this diagram here. Current is flowing in this direction, right? So we can call this like, and magnetic field is, there is a voltage that is set up that is mutually perpendicular to the voltage. So what I mean by this one is perpendicular to the electric field. I mean that electric field. So 1 over any J cross B is talking about the electric field in this direction, while the electric field in the direction of electric field is M over N E squared tau times current density. So this is the direction of current. This is direction of bulb. In a direction that is perpendicular direction of electric field. So, and this is field. It is like in the direction that is perpendicular to the same as okay, so have you all effects is just the direction that is perpendicular to both material. So the voltage that is so when we are talking about all voltage, we also talk about all resistivity. Because of time, please let's I'd advise you read this at your own time, and if you have questions, we can talk about them in details. So in conclusion, from Dirac theory, we can say that the all coefficients R subscript H is defined as -1 over NE. So this allows us to measure the density of electrons in metals, and Dirac theory gives reasonable results for many metals, and it's good for describing semiconductors. And radial scattering time is obtained to be in the order of 10⁻⁻14 seconds for most metals near room temperature. So then let's talk about some things that after assuming that radial theory was successful, then they went ahead to do some calculations with radial theory. And one of it is thermal conductivity in equation 39. The thermal conductivity in equation 39. So CV is the specific heat capacity of the particle. V is average thermal velocity, which is also, now we have the scattering length, which is also defined as the product of scattering time and the average thermal velocity. So we can recall our equation 3, which is the specific heat for a monatomic gas. And also, this expression is which is the average thermal velocity. Have we seen it before? Have you seen this equation before? This equation 40.
No, sir.
Okay.
No, sir.
Okay. So the average thermal velocity, for now, let's just take this as the average thermal velocity, which is defined as equation 40. And our interest is equation 39. And now we are going to substitute this expression 40 into 39 to have a cleaner expression for thermal conductivity. So we'll be talking about conductivity. We should now begin to specify electrical conductivity, thermal conductivity, because today we're talking about electrical conductivity, sigma. We said sigma E is equal to the current density. So, but now the conductivity we are talking about here, kappa here is thermal conductivity. And when we substitute V in the earlier equation, we have this value. So, but we've spoken about Lorenz number, right? Hello?
Lorenz Force, sir.
No, we haven't.
Lorenz number.
No, sir.
Okay. That means we still have a long way to go then. So Lorenz number is like saying we are trying to divide the thermal conductivity by electrical conductivity. So Lorenz number is L. This is not Lorenz. This is not the Lorenz force. This is not having T. Lorenz. So it is thermal conductivity divided by the electrical conductivity at a certain temperature, T. So from this expression, we know kappa to be our thermal conductivity from the previous equation. We also know sigma to be our electrical conductivity from which equation is that now? But we've seen that today.
Should be 36.
This is 36. And now we are to talk about Lorenz number. So by from this expression 42, we can easily say that the Lorenz, because when you look through these values, they are all a bunch of constants. Pi is a constant, Boltzmann's constant is a constant, electronic charge is also a constant. So we can arrive at this value. but we should not forget that something happened along the way. And what happened along the way is this expression of V. Because when you look at this V, we are talking about average thermal velocity. And we are talking about average thermal velocity. The way it is calculated is to say you have different particles in a box, they have velocities, you want to calculate their average, something like a root mean square problem, in which you will say, I'm calculating the square of each of the velocities of the particles, and I'm now finding the average, then I'm now finding the square root. There was a problem when they obtained this value. They noticed that there was a slight difference in prediction, and they realized they have used V squared, not so what they obtained at that V squared is like saying that I've calculated the velocity of each of the particles in the box. I'm now finding the average. That is what let me put on the spotlight. This is saying that I've calculated, I want to find the average of the velocities of particles in a box. This is saying that I've calculated the average of each of them. I'm now squaring. But there is also an alternative here, which says that I've calculated the square of the velocities of each of them. I now find the average. I've calculated the square of the velocities of each of them, then I'm finding the average. This is saying I've calculated the average velocities of each of them, and I'm squaring it. So this statement became confusing. When you are trying to get a particular value and you are not getting what you have to get, you start thinking of how to squeeze it in. So then they now recalculated by saying, since we have used the square of V, average V here, let us also find the average of V square. And they got a figure that is still close enough. So metals have approximately the same Lorenz number, and that is Wiedemann-Franz law, that metals have approximately the same Lorenz number. Let me check something, please. Okay. I'm just surprised we are hearing Lorenz number for the first time. I wanted to say, no, that is wrong, that we have mentioned it before, but I see that I'm wrong. Okay. So I got this table from one of the recommended books. The valence numbers obtained from Drude theory, and this is Lorenz number obtained from Drude theory. RH is all coefficients. coefficients up to end the call. So table 1.2 tells us that the calculation of Drude theory agrees with Wiedemann-Franz law. And what is Wiedemann-Franz law saying? Wiedemann-Franz law is saying that metals have the same Lorenz number. That is, metals have the same ratio of thermal conductivity to electrical conductivity at certain temperatures. So that is what Wiedemann-Franz law is saying. And Drude theory, from these values, though, we have some, when you look through, we have some exceptions here, but we can still say that it has been able to predict fair enough that the Wiedemann-Franz law. So there is also another property, which is thermoelectric properties, and it works with the principle that when you pass currents through a particular material, it will also drive it through the material. So you're saying that you have a certain material, and you drive electric currents through the material. There are some materials that have good thermoelectric properties in which, with time, this place will become colder and this hotter. So it's like driving it as current is moving. It also pushes away, pushes it through the material. It drives it. So, and it is used in refrigeration devices. So, and that takes us to what we'll be talking about, which is the Peltiers Coefficients again. So there are many names you have to talk about here, one of which is the Peltiers Coefficient. The Peltiers Coefficient is defined as big theta, while JQ and J is the heat current density, and J is electrical current density. So a material that for a good thermoelectric device must have high Peltier's coefficient and low resistivity. So when a material, I will say we are driving current through a particular material, we should also remember that there is also something called electrical power, P, which is equal to IV, or better still, we say I square R. When you are driving current through a material and you begin to increase the current, I square begins to become very large, and becomes very large, the material begins to generate it. But when R is very small, and I square is growing, then the power the heat generated would be very small. So a material that has a large R and a small theta will be a very poor thermoelectric material. So for a material to be a good candidate for thermoelectricity, it has to have a small R and a big theta. So from kinetic theory, thermal current is defined in equation 44. And when you look at that, it resembles the kinetic theory of gases, where you start by saying 1/3 something. So, and in this place, CVT is the heat carried by one particle. So, and the Peltier coefficient the Peltier coefficient, we have defined the Peltier coefficient earlier to be in a bunch of equations here we say, so the Peltier coefficient here is theta. So, and that should be J raised to power Q divided by J. So, and that is what we have here. The Peltier coefficient in, the Peltier coefficient J raised to power Q divided by J is what we have in equation 45. Then another coefficient, the Seebeck's coefficient or thermal power, is also given in equation 46. So Seebeck is S, and that is equal to pi over T. So it's just like a T with 2 legs divided by a T with 1 leg, and that is exactly what we have here. Divided by T should give us what we have here. Since S is pi over T, so this expression divided by T gives us another constant, which is equation 46.
Excuse me, sir.
Okay.
Yes, sir.
The Peltier coefficient, the symbol you
Yes.
use, you'll be calling it theta before, but when we come to Seebeck, you say
sorry. It is pi, not theta. It is a capital pi. I'm very sorry about that. The pi, small letter pi. So sorry about that. So for most metals, the actual value of the Seebeck coefficient is a ratio. For most metals, the actual value of this ratio is 100 times smaller. This means that CV for an electron is much smaller than 3/2 kb. So that is even one problem on its own. We are trying to deal with electrons as if they are monatomic gases. And in the course of trying to deal with electrons as if they are monatomic gases, we required the specific heat capacity. And we don't know the specific heat capacity of electrons. Then we went ahead to use 3/2 kb, which is the specific heat capacity of gases, not electrons. So 3/2 kb has been used by Drude theory to determine 3/2 kb has been used in place of specific heat capacity of electrons, whereas this is specific capacity of monatomic gases. So for that reason, we can say that something is not right, because for most metals, the Seebeck's coefficient is 100 times smaller. This means that CV for an electron is much smaller than 3/2 kb. So Drude theory has succeeded in predicting many transport properties such as electrical conductivity at finite frequencies. However, the wrong prediction of Peltier's and Seebeck's coefficients by a factor of 100 can be classified as a failure of Drude theory. And it will surprise you that the Drude theory predicted the Lorenz number conveniently, or let's say that it predicted the Wiedemann-Franz number correctly, because when we spoke about the ratio of thermal conductivity to electrical conductivity, we found the values to be constant for metals. So Drude theory was able to predict that conveniently, but failed to predict the Peltier's and Seebeck's coefficients. Then we should ask ourselves, what went wrong? Why? How? And I'm sure you won't be offended again that why are we learning this if it will not predict the Peltier and Seebeck's coefficients correctly? So then that's the question. How did Drude theory predict the Lorenz number successfully, but failed with the Peltier and Seebeck's coefficients? So the answer is goes follows that in Drude theory calculations, we have used specific heat capacity that is too large for electrons. The specific heat capacity we have used is too large for electrons. That is CV over N is for CV over N. That is the specific heat of electrons. I think I should change this from the specific heat for electrons should be very small compared to 3/2 kb that is being used by monatomic gases. And we have also used a velocity that is too small. So in this expression, in Drude theory, we have used CV over N for gases in the place of CV over N for electrons. So we have used a CV over N that is very big. And we have also used a velocity that is very small. So the reason why it was able to predict Lorenz number successfully was because two errors canceled each other. This value is very small, while this value is, the value we used here was too big, while the value we used for V square was too small. So it's like when you are in the exam hall and you make one mistake, you wanted to write 10, you wrote 100, and you moved ahead, you were calculating, you wanted to write 50, you wrote 5. You now got to a point, you now said, that's your 100 divided by 5. Then 2 errors, they'll cancel each other and you still get the same thing. Or did I say it correctly? You wanted to write 100, you wrote 10. You wanted to write 5. Okay, you wanted to write 100, you wrote 10. And you wanted to write this wrote 0.5. So by the time you now say you are dividing, you still have the same value. And so 2 errors canceled each other in the calculation of Lorenz number, and they did not cancel each other when it was time to obtain Peltier and Seebeck's coefficient. So when you look through the our derivations, you can look out for where exactly did we use CV over N and V square. Where exactly did we use CV, and where exactly did you use this average velocity in the same expression while dividing? So another thing that you should also take note is in this work while we're discussing is that we spoke about electrons like gases. Electrons are fermions, and they have to obey Pauli's exclusion principle. Electrons are fermions. They have to obey Pauli's exclusion principle. So you cannot just pack a bunch of electrons together and say, without even mentioning what is their state and things like that. So one beautiful thing that's also in this history class is that Sommerfeld came about and applied Fermi Dirac statistics. He applied Fermi Dirac statistics to we applied Fermi Dirac statistics to the work of Drude. So this work of Sommerfeld came shortly after Fermi and Dirac derived Fermi Dirac statistics. And shortly before then, Pauli have discovered the exclusion principle. So his own work was to now notice that Drude did not even consider this principle and these statistics in his work. So Sommerfeld came about and applied Fermi Dirac statistics to what we now call free electron theory to study electrons in metals. So briefly, we can talk about Fermi Dirac statistics. Given a system of free electrons with chemical potential, the probability that an eigenstate of energy E is occupied is defined by Fermi factor n subscript f. So the probability is what we'll be talking about now, the probability that it will be occupied. The probability that an electron state, that an eigenstate will be occupied is defined as n subscript f. And that probability is defined as 1 divided by exponential everything we have here plus 1. And everything we have here is talking about the energy of that state that we are talking about, that is it occupied or not, minus mu, which is chemical potential, divided by kBt, which is Boltzmann's constant, at a certain temperature. So the probability that a particular energy state will be occupied depends on the energy of that state. It depends on the temperature you are considering. And it also depends on the chemical potential. So what you have here, it is not a product, it's just saying that the probability as a function of this, it is not, these two terms are not multiplying each other. It's just saying n of f probability as a function of what we have here. And when we are talking about probability, it should range from 0 to 1. So what you have here are things I expect you should be able to read on your own, but I'm more interested in discussing this about Fermi Dirac statistics. So this is a graph of NF against energy E divided by Fermi energy. Fermi energy. So we'll be talking about different types of Fermi now. Fermi energy is like an energy such that every energy level below the Fermi energy is said to be completely occupied at 0 Kelvin, while every energy that is greater than the Fermi energy is said to be completely empty at 0 Kelvin. I'll say it again. Now, we are talking about 0 Kelvin. Let's call this line, assuming this line is talking about energy. This is energy. So energy, okay, energy over Fermi. Okay, just think about this line to be energy and this dotted line to be Fermi energy. So at 0 Kelvin, all the energy states that is below this line will be completely filled by electrons, while the energy states from this dotted line and above will be completely empty. Well, this is, so now let's look at this again to say this axis here is telling us that this axis is for probability. It should range from 0 to 1. So when it is 0, it means it is not occupied. When it is 1, that is no longer even probability itself. It is telling us for certainty that it is occupied. So at this point, is occupied, it is occupied as the energy. So as I'm moving now, I'm moving as energy is increasing. It is completely occupied, completely occupied. Then we now start saying probability is reducing. We are not sure, is it filled or empty? Probability is reducing. Is it? So when we get to this stage and we're talking about the energy level at this point, we can say with good certainty to say that at this point, the energy level here is completely empty at 0 Kelvin. It's completely empty at 0 Kelvin. So let's leave that graph and talk about these two graphs. They are saying the same thing. They are saying the same thing. So one thing I want you to notice that this line here is telling us that at 500 Kelvin. This is also telling us that at 5,000 Kelvin. This is telling us at 10,000 Kelvin. This is telling us at 25,000 Kelvin. So you'll notice that as the temperature is increasing, this is no longer, it is becoming slant. It is no longer like a step. What we have like this is called step function. But when it is becoming slant like this, it is said to no longer be a step function. And another language that is often used is to say that the step is smearing out. We can say the step is smearing out. So let me draw with my pen here to say that what will be at 0 Kelvin. At 0 Kelvin, I will expect something like this. Get to this sharp corner, come down straight. Come down straight. And get to this place and move straight. So at 0 Kelvin, this is what we have. At 0 Kelvin. At 0 Kelvin, it will be having something that is, we will be having the states below this Fermi energy. This blue line, the vertical blue line, is the Fermi energy. So that at 0 Kelvin, everything below it is completely filled up. So the probability that it is having an electron is 1 at 0 Kelvin. Well, okay. So while every energy level above this is completely empty. So you can see after this point, we said the probability, it just drops down to 0. When it drops down to 0, everything we have here, every energy above this is increasing energy. Every energy we have here would be empty. That is, it will not be occupied. N of F will be, N subscript F will be 0. So it will be empty. So it's now easy to look at it that at 0 Kelvin, it is like a perfect step. At 500 Kelvin, the step is smoothing out, is smearing out, and 5,000 Kelvin, somebody is saying it's not getting the explanation. Please, if you have any question, unmute yourself and let me know what exactly you are not getting, because I'm taking my time to say this slowly. Unmute yourself and let me know the problem.
Yes, sir. That straight line, I start from 5. We're talking about at 0 Kelvin. And all
Is
those
it this
keys
one? Is it this B, figure B I'm talking about?
Yes, sir.
Okay, I'm starting from what?
Yeah, from that 5, there's a line that tends towards the one in the NF, the Fermi energy. From that line of Fermi energy. So
okay, this is the Femi. This is the Femi energy.
Yes, sir.
Okay.
So you were talking
I'm
about
listening.
So we are saying it is completely occupied from that
Okay.
Fermi energy.
Okay.
So
okay.
My question is what are the significance of those 500K, and what does that K stand for? Are those K temperature or what?
Yes, they are temperatures. This is 0 Kelvin. 500K is 500 Kelvin. Were you thinking of 500,000 naira?
No, sir.
500, 0K, 0 Kelvin, 500K, 500 Kelvin, 5,000K, 5,000 Kelvin. So, do you still have questions?
Yes, sir.
No,
Or I
Yes,
should
sir.
go ahead? Okay, continue.
Now, yes, sir. You were talking about N subscript F as Fermi
Okay.
Energy, and you were also talking about
No,
a
wait.
property.
Wait. I spoke about N subscript F as Fermi factor. I spoke about N subscript F as probability. That it will be occupied.
Yes, and that is what I want to ask.
Then hold on, please. I also spoke about E subscript F. E subscript F as Fermi energy. Okay, so continue.
Right, sir. And I'm thinking that since we are having temperature and there's a variation due to temperatures, they are becoming more smearer. So I want to ask that, is it possible to have a negative temperature? And if possible, that we have negative temperature on this Fermi factor ranging from 0 to 1. I'm seeing that beyond it, we still have 1.2, but in probability, we don't have anything more than 1.
Okay. Yes, in probability, we don't have anything more than 1. The maximum is 1. The 1.2 they put there is just to show you that there is nothing else to that. They did not just stop at 1, that anything between 1 and 1.2 is empty. So probability ranges from 0 to 1. And about temperature, at absolute temperature, 0 Kelvin is the least temperature that is attainable according to science for now. 0 Kelvin is the least attainable temperature. Can I even call it attainable? It's the least temperature. So there is nothing like, if you remember, is it from Charles' law, how they obtained 0 Kelvin to be minus 273.15 degree Celsius. They plotted a graph, they extrapolated to cut a vertical, an horizontal axis at a 273.15 Kelvin. So anything below 0, it's Kelvin, is not physical. It is not for now. It is not known. So the least temperature is 0. I hope that is also clear.
Yes, sir.
So when we are talking about energy levels, maybe we should think about it in this way, that we have some energy. Okay, let's say we have some E0, E1, E2, E3, E4, and at a particular point, let's say this E2 is our EF. That what is telling us that the energy levels here, they have electrons. That is the orbitals here. They are completely filled with electrons. If it is 2 electrons per orbital, it is having 2 electrons. But as at, so this is our EF, right? E2 should be our EF. But everything above it are also energy levels. But at 0 Kelvin, they are completely empty. So, but as temperature begins to rise, some electrons will begin to escape from this point. They'll begin to appear here. Some will begin to appear here. Some will begin to show at higher levels. And as they are showing here, they are not coming from 0. They are as they are appearing here, it means they are leaving places at energy levels about the surface. So when we are talking about 500 Kelvin, for instance, and when you look at this 500 Kelvin, it's at this corner. Let's assume electrons are filled up. Let's assume electrons are filled up in everything in this box, in this square at 0 Kelvin. At 500 Kelvin, some electrons escaped from this corner. And where did they go? They came down here to occupy this corner. At 5,000 Kelvin, some electrons that were here, they received sufficient energy from the fact that they were exposed to higher temperature. And where did they go? They escaped to this part to occupy this part. So the area of the shape you have here for 5,000 Kelvin, the area of this shape you have outside the graph, but within the scope of Fermi energy, is also this area of the shape you would have here. So it's telling us that the area under this graph, at 0 Kelvin is equal to the area under the graph at 500 Kelvin, is equal to the area under this graph at 5,000 Kelvin. So it is so the area under the graph can give us information about the number of available electrons. So the number of available electrons at 0 Kelvin is also the number of available electrons at higher temperatures. The number of available electrons we have at 0 Kelvin is also the number of available electrons we have at higher temperatures. But some of the electrons, as temperature increases, they gain energy. They gain energy and jump above the Fermi energy, and they occupy higher energy levels. Do we still have a question with that? Do you have any question on Fermi Dirac distribution? I will take silence to mean no. So,
No question, sir. No.
okay. I'm listening. Please go ahead.
Yes, sir. Actually, I can't say I really fully understand, but I heard everything, sir. Is there any other way, like any other way we can get all this graph more pictorially, all these things you are saying, sir?
The graphs I put here, I got them from Simon 2013 and Kittel. I've given you recommended textbooks before. So if it's more pictorially you want, go to the recommended textbooks, get books on solid state physics. And so that would, when you get books on solid state physics, if it's pictorially you want, fine. But I think I've been able to tell you in Nigerian English, in our pidgin language or our dialects, pictorially. So if there is any question that is not clear now, maybe I hope this recording is successful and I'm able to upload it on our YouTube channel. So, but maybe when you listen to it over and over again, it will stick. But the long and short is saying that this column is talking about probability, while this column is talking about energy. So, and as I'm moving in this direction, I'm moving in increasing energy. As I'm moving in up like this, I'm moving in increasing probability. And these graphs, you can also follow them from their origin to their destination to say that anything below this graph is telling us like a fraction of probability that what is probability? So what's probability that at this point at energy E over KB equal to 4? Is it occupied at 0 Kelvin? Yes. Is it occupied at 500 Kelvin? Yes. Is it occupied at 5,000 Kelvin? Yes. But it is not completely occupied at 5,000 Kelvin. it is partly occupied at 5,000 Kelvin. So is it occupied at 10,000 Kelvin? Yes, but it is not as occupied as it was in 5,000 Kelvin. So let me leave you to this graph. If you had gone through this graph before now, we won't be wasting time on this. But I would like us to end this class in 5 minutes, because I know you have another class, and you may want to refuel your stomach and while refueling your batteries. So, but I'm still open to questions right now on this one. If there is any question you want to ask, please do. Going, gone. So on this graph up here, we spoke about mu to be approximately Fermi energy. Mu is chemical potential. While E is Fermi energy. Chemical potential is equal to Fermi energy at 0 Kelvin. Chemical potential is equal to Fermi energy at 0 Kelvin. And what's going on? So chemical potential is equal to Fermi energy at 0 Kelvin. So what else do we need to say here? And yes, we should also mention this. There is also a margin here. No, sorry. When you look at this KBT, is telling us that from this point where the smearing started to the point where the smearing ended is equivalent to KBT. So let's come down again and look at that's our graph. That's our beautiful graph. For 500 Kelvin, the smearing started somewhere here and it ended somewhere here. So we can say this point is from this point to this point. The energy difference between this line and this line is KBT. KB is the constant, T is the temperature. Now I want to talk about if it's at 0. Hello, can you hear me?
Yes, sir.
Yes, sir, we can.
Okay. Because I'm receiving a message from one of your classmates on Telegram right now telling me you are having glitches. So that I will not be the only one talking to myself. So if you're having glitches, I'll go to the YouTube page and pray that if this recording is successful. So, okay, so before I was interrupted, sorry. At 0 Kelvin, like I told you before, the KBT will be equal to 0. As temperature increases, when T is 500, we'll be having 500 kb. By the time T gets to 5,000, we'll be having 5,000 kb. So as we're having 500 kb, 5,000 kb, for 5,000 kb, this is where the smearing starts. And this is where the smearing ends. Somewhere here. For 10,000 kb, for 10,000 K, sorry, the smearing starts somewhere here, and also ends. So the difference between the time smearing starts to the time where smearing stops at a certain temperature, the energy equivalent is KBT. So I think that also explains that as temperature increases, the step disappears and the step becomes the step function becomes smeared. So I think I've said everything I have to say about these graphs. let me see if there is any other thing I should mention. Okay, so I would advise to read through these materials. We have a Fermi wave vector, Fermi momentum, Fermi velocity. When you come back here, you talk about Fermi radius, Fermi surface, Fermi sphere. So if you are not happy hearing the name Fermi, you better start liking it now, because even in your sleep, you will still see some Fermi angels coming to visit you. So everything on these pages, I think they are very smooth and straightforward. Let me just see if there is anything I should mention before we leave. Okay, I think we have to stop here. I will try to make a video in your absence about the remaining part of this lecture, and also put on YouTube as early as I can, because there are also a lot of work for me too. And I would also try to update this our courseware on the LMS, because currently it is having just chapter 1. So I would try it contains chapter 2 before the week runs out. And when I do that, I will send you an email so that you go to the LMS page to download it as early as possible. So I would have to end the class here if there is no question. Is there any question? What do you say? I'm listening. I'm listening. If you have a question, you can speak.
No questions.
Okay, and the assignments, the assignments I gave you, I would like to have them by, let's say Saturday by 6 p.m. Saturday by 6 p.m. Send it to the email address for the course, which is physics 307 at
Is it a
STU.
scanned document or?
I don't expect you to send scanned documents now. I expect you to type it and upload. You can always type in the Microsoft Word or documents and
Yes, sir.
not scanned.
Yes, sir.
Not scanned.
Can we not write and then scan it?
No, I don't want that one. It will not,
You know,
I can't be downloading many photographs.
the symbols may be somehow the division, the bracket, the
everything on this page, I typed them. Everything in this book, I did not scan them. I typed them. So if I tell you to just move from one equation to the other, I don't think that should be a problem to you. That is also part of learning. You should go and learn how to type equations. That is why I put it on Friday. I'm not used to giving assignments and tell you to submit after a very long period. So go and learn how to.
Service, can we also submit before Saturday?
Sure. You can submit right away. So go and learn how to type equations. You are a science student, and the world now should not. So have a blessed week.
And you too, sir.
Thank you very much.
Sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you all. Thank you too.
Thank you for your time, sir.
Thanks for your time too.
Thank you, sir.
That's what you do.
Thank you, sir.
Sir, can we get the YouTube link?
I will put the YouTube link on the LMS page, so you can just click and get to the you click the link and get to the YouTube straight away from LMS page.
Okay, sir. Thank you, sir. Thank you, sir.
So as you are watching, also subscribe so that by the time I start putting some other contents there, you should also. I may not mention that it will be
No
out
problem.
of the class, and I'll make it
Sir.
public. Okay.
Okay, sir.
Bye bye.
Thank you, sir. Bye bye.
Thank you. Bye.